Greetings, folks. Professor Fiore here, and today's topic is on DC Delta-Wye conversions. What are we talking about, Delta-Wye conversion? Well, it turns out that there are certain circuits that you cannot solve using just series parallel simplification techniques. Here's a quick example. We have an H-bridge configuration. There's nothing you can do here as far as adding resistors in series or resistors in parallel that's going to simplify this any more than it already is. All right? R1 and R2 are not in parallel because R3 is in the way. Same thing is true down here with R4 and R5. But you can't say that R2 and R5 are in series because, again, there's this path over here for R3. You can't get any simpler than this. Now, there's a bunch of different ways you can solve this, including mesh analysis and nodal analysis, but I want to look at this idea of a Delta-Wye conversion. And it allows you to take a three-terminal network and sort of rearrange the elements in it, the components in it, changing values, and you come up with something that is functionally equivalent. And that functional equivalence may be such that you can now apply series and parallel simplification rules to solve the circuit. So here's really what we're talking about. A delta configuration, a Y configuration. These have different names. Sometimes you'll hear this referred to as a T configuration, if the two top resistors are drawn across. Sometimes this is referred to as a pi configuration if these two on the bottom here are drawn straight up and down because it kind of looks like the Greek letter pi. And, Y, W-Y-E, sometimes it's just Y, the letter Y, which is the shape. And, somebody had to get smart about it, I guess, and call it W-Y-E instead of just using the letter Y. Don't ask me. And, of course, sometimes you'll see the Greek letter delta here for the word delta. But, it's all referring to the same thing, right? So you got 3 points on here, points X, Y, and Z. And if you use the right values, starting with RA, RB, and RC, and you convert them over to RD, RE, and RF, you can replace one with the other. So I have a set of equations over here to go from the delta configuration to the Y configuration. And there's another set of formulas to go in the other direction, to go from Y to delta. And the proofs for this is all found in the DC textbook. And remember, you can download that for free. Just follow the links in the description of this video. And if you want a hard copy, you can get a cheap, inexpensive 8.5 by 11 format hard copy up at Amazon. Again, follow the links. So all we really have to do is follow these equations and sort of do a substitution here and see what we come up with. Okay. Notice the denominators for these are all the same, RA plus RB plus RC, in other words, the sum of these. And then really, it's just a product of a couple of resistors in the numerator. So for example, for RD, what you're thinking of here is the resistors that are on either side of it, RA and RB. If you're looking at RE, either side of it's RA and RC. If you're looking at RF, either side of it's RB and RC. So we can just plug numbers in here and come up with something. All right. All right. So, that's fairly straightforward. I wouldn't say it's trivial, but it's a fairly straightforward process. Okay. So how does that help us over here? Well, think about it. If we were to take these three elements on the bottom, which I've conveniently labeled R3A, R4B, and R5C, corresponding with the A, B, and C that we saw right down here, right? There's the A, B, and C. So what we wind up with would be three resistors, right? There'd be one here that would be connected, and the third resistor would come down here, okay? Why does that help? How is that any better? Well, let's take a look at it, okay? So I would take these three resistors, the 30, the 40, the 50, plug them into that set of equations that I just showed you, and we would come up with three new values for the D, E, and F, as it were, which is this. Okay, so here's those same 2 points, and we had R3 up here, and then the R4 and R5 over here. So that was the delta configuration. This is the Y configuration. I know it's drawn a little weird, but this is your Y. Kind of a blocky looking Y, but nonetheless. So here's RD, RE, and RF, functionally equivalent, right? So again, just to jog the memory, right? There's RD, RE, and RF, the equivalent. How does this help us? Well, when I look at this, I can say that R1 and RD are in series. Add them together. I can do the same thing with R2 and RE, right? Those are in series. Add them together. Now I have a resistor and a resistor. Those two are in parallel. I can put those in combination. Once I have that, I know that's in series with RF, so I can do a bunch of different things. I could, for example, find the exiting current over here. Doing that, I could do a current divider, find this current, and then I could find, using Ohm's law, the drop across R1 and R2, subtract that from the 10-volt power supply, and I would have my two nodes of interest, Vx and Vy. Now I've denoted this with a C on here to indicate this is the converted version versus an O in the original version, right? And basically, if this is correct, then when I do a simulation on here, I should get the same values, same voltages for Vx and Vyo, the original, as I do for Vx and Vyc, the converted, all right? This, you can whip out your calculator real quick and boom, 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 come up with some answers, right? This one, not directly, at least not doing series parallel conversion techniques. You're stuck, right? Like I said, there are other things you could do. You could use mesh analysis or nodal analysis, but, you know, as is, you're kind of stuck, all right? So let's just do that. I've done the computations for the 30, the 40, and the 50, and it happens to work out to 10, 12 and a half, and 16 and 2/3. So we're going to get a real tiny little error here because this RF should be 16.666666666, you know, out forever. So I just have to round this off to 16.667. So, you know, maybe a fifth digit here and there might be a little bit off, but let's just see what we get. So I'm just going to come up and do a DC nodal voltage thing over here. I'm not even going to use the probe. I just want to see what my Vx and Vy are. So I get 7.8689 and 7.377. All right, that's my original circuit. So keep your mind on this VXO, the original, 7.8689. So let's flip over to our converted circuit. 7.8689. And then the Vy, 7.377. Converted, 7.3771. All right, there's that little fifth digit that I was talking about. We got it. It works, right? So you can sit here and play with the power supply. You can change the values of R1 and R2. So we could come in here and, you know, change R1 to, you know, 15 ohms, let's say, and R2 to 36.9 ohms. As long as you do it in both of these, right, do it in the original and the converted, you should just get the same values. So one is sort of plug compatible with the other, right? And there are instances where we want to go the other way, where we have something that's, you know, not exactly this, right, because this is solvable as it is, but there would be considerations, places where you'd say, well, geez, I would find it more convenient if I had this situation turned into, you know, this situation, because maybe, you know, maybe I've got a resistor across here, and that's going to, you know, complicate things. So I do it like this, and, you know, maybe it's going to work out better for me. You know, all depends on what the rest of the circuit looks like, obviously. But I'm just saying, there are instances both ways, right? That's the thing, you have to look at it. So you can do delta to Y or a Y to delta. Again, if you want the lowdown, the nitty gritty, how did these formulas come about? Because, you know, I hate to just throw formulas out here. Just a little bit too involved for me to go through here in a video to prove it, especially when you got a free textbook you can download, right? So it's all there. Just follow the link. If you don't have the textbook, follow the link in the video description, and the proof is all laid out both ways. All right? Okay, so this is a little something to play with. It's really nice to do in the simulator because you can play with the numbers very quickly, put it in different situations. And, just to be clear about this element here, this little 3 resistor element that we're converting is ground referenced. It doesn't have to be. Right? That doesn't have to be the case. If you're thinking, oh, it's got to go to ground. No, it doesn't. Matter of fact, you could, instead of doing it this way, we could have solved this by converting these 3 resistors on top, because that also creates a delta. And then over here, I would have had, 1 resistor coming off here, 2 resistors, and then the original 2 resistors I had on the bottom, right? The R4 and the R5. So it's flexible. Doesn't have to be ground reference, doesn't have to be going to a power supply, it could be in the middle of something. All you need is 3 discrete connection points, right? 3 discrete connection points. And you swap one with the other. And there you have it. All right, have a good one.